All right, hi, good evening, everyone. We're almost there. This is the last one. My name is Atin. I'm one of the founders of this company, Galileo. And we've squarely been in the language modeling evaluation space since our beginning, which was about 3.5 years ago. And a little bit about me, I've been in the machine learning space for about 12 years now. I was a senior staff engineer at Uber for many years and helped build out some of their initial AI infrastructure. Some of you may have heard of Michelangelo, which is Uber's end-to-end machine learning platform. I was one of the architects and early engineers on that, and we built out the first feature store back in 2017, and a lot of tech, which is kind of become MLOps standard. So a lot of lessons learned over the years. And we started Galileo about 3.5 years ago at this point, and we ended up at a lab at Stanford, sort of building the prototype. It was a language modeling lab. And similar to what Bob said back in 2021, when you hosted a webinar on LLMs, close to 0 people showed up. And we had one of the investors who said that you're in deep learning models because it's cool. So that has certainly changed quite a lot. And the last 3 odd years have been a great journey of sort of pivoting into eventually generative models. But we literally started off with the thesis that evaluation tooling for machine learning was broken. I saw that firsthand at Uber. And the reason was that you would take models and you would take evaluation data sets and you would compute F1 or RMSEs, and you would say, yay, this is great, I'm going to productionize it, and that's it. And then a lot of issues were because these kind of metrics, they're statistical in nature, and while they're necessary, they're not sufficient. They treat all kinds of errors the same way, and they rely on this eval set that you've curated manually. So it's very myopic in nature. So that was the thesis of the company. We started off building Galileo as a fine-tuning language modeling platform back in early 2021. So we would do like classic NLP use cases, text classification, entity recognition. But the whole tool would essentially hook into your PyTorch and TensorFlow models, and it would literally sniff out the logits and see how they converge to the labels over all the epochs. And we would apply statistics and give you errors in your data, which was bringing the model down. So that was the whole hypothesis. And we were dragging our feet for about a year or 2 before LLMs picked up. But evaluation became an even stronger need and a bigger need because these systems, these LLM systems, they're even further more black boxes. They're hard to predict. And we've already seen a lot of people talk about just the lack of predictability, which to some degree infrastructure like vector stores, et cetera, try to solve. But despite that, there's still a severe need for evaluation tooling. So enough about the company. I'll get into what I'm going to talk about today. So there's 2 topics I wanted to cover today. And this is primarily based on a lot of the lessons that we've learned in the last about year or so of working with very, very big customers. We've had the privilege to work with JP Morgan, Comcast, Procter & Gamble, and many other such big companies, and help them productionize very high quality LLM applications. And what we've seen is that there's essentially 3 sort of phases in LLM system building. Of course, the first one is sort of on the pre-prod experimentation side, where you're essentially evaluating your, of course, the models that you want to use, but along with that, a lot of other data which is kind of surrounding your models, including the prompts, including your vectors and from your vector store, including the chains that you're computing. But essentially, your goal is to come up with the ideal sort of combination of prompts and vector store hyperparameters and the like that gives you like an ideal system to build. Then you productionize your app, and it goes into sort of the monitoring stage where of course, hallucination is sort of a big problem, and I'm going to talk deeply about hallucinations. We've been doing a lot of research on it for over 18 months now at this point. So the second part of my presentation is all about that. And the last part is a need that we've seen emerge more recently as systems have started getting productionized, which is the ability to essentially real-time intercept responses from these systems and sort of steer your LLMs to safety in real time. So how can you build a system which allows you to define certain rules and sort of plug them into your system so that you can sleep at night knowing that your chatbots wouldn't be, selling your Chevy for $1 and those kind of things. So here, this is essentially going beyond evaluation and observability. And the reason for going beyond that is because, of course, they're necessary, but they're very reactionary, right? Like you can observe those squiggly lines in a monitoring tool and get an alert in your PagerDuty, but by that time, the damage is already done. Especially with LLMs, it's become a more serious thing because pre-LLMs, sure, you might have your recommendation system model and it might give you a bad prediction, but so what? You might see like a McDonald's ad on your Uber Eats instead of something you ate yesterday. But that's lesser of a threat than some of these chatbot systems where literally the output of AI is the product. So that's why interception becomes a very big thing where the need for redacting hallucinations in real time is a very big need. And steering your bad responses, of course, it depends on detecting them and then sort of doing auto retries when, say, something like your agent's task completion rate for that request is low. So all these kind of actions become super important. So this is a trend that we've seen very, very recently in the last couple of months, really, where the need for interception in evaluation has emerged. So just a high-level view of the systems flow. Like you have the query on one side, the LLM system. This is, of course, very high level. So if you really dive deep, you have all the infrastructure within the LLM system box. But then you get the response from it, and then you plug that into your application's response. But there's a lot that can go wrong in real time, both at the input and the output level. In the input, you can have prompt injections, which is a very common issue that we've seen in enterprise. Jailbreaks, leakage of any kind of PII data, as well as on the output side, of course, hallucinations and embarrassing mistakes, et cetera, which eventually sort of bring the performance of your LLM systems down. So this is where our Galileo's Protect module comes in. And this is sort of an animated showcase. I don't know why this GIF is not working. Oh, it might be because it's a PDF, but I can walk you through what it would have been. Essentially, it's a chatbot system, and there's an output of the application which gets intercepted, and you apply a bunch of metrics. Now, metrics is very key to our platform. It's essentially, if you could summarize Galileo, we're essentially a metric store, and we're a metrics company. And a lot of these metrics are driven by a lot of research we do. But those metrics would detect prompt injections and detect hallucinations. And then from there, you build like a spec-driven system or a rules-based system, which would allow you to, say, redact PII from the response or have some boilerplate response if there's a hallucination which is detected. Maybe this would paint a better picture here. So this is kind of what we've seen the workflow emerge in people who are actually building real LLM systems which are productionized. In the dev environment, you have the notebook where these LLM experiments are done. The application code is written on the side, which is the real chatbot code. And then you have, we offer an API which allows you to, say, create a rule that if, say, the hallucination score, say a score between 0 to 1 is greater than 0.5, you want to have a boilerplate response, or you want to do a retry. So those are the rule sets which get authored. Similar, you can author them in one of many ways. You can write a YAML, you can write, essentially just write code, and you store them in a centralized store of rules, which gets applied and utilized in real time. And then you get kind of like a control plane, similar to, say, you were to manage configs in real time in your ops system. It's very similar. So there's a lot of similar workflows when you're sort of monitoring, say, real-time configurations in your application. Here you can see how it looks in code. So in Python, you can define a rule set where The rule can be the name of the metric. And Galileo offers out-of-the-box metrics backed by our research, but you can create your custom metric. You can write a Python function and register that as a custom metric. And you register the rule, and you can continue defining your rest of your LLM system. In this case, you can see that it's a LangChain system that I've built over here. And then you essentially just apply those rules to your chain. And what would happen is, say if someone did attempt a prompt injection, it would get immediately detected and automatically your response would be adjusted. So this is one part of what I wanted to talk about. There's a couple more things. This is how the UI would look. And this is Galileo's UI in real time, where you essentially get for every single request, you can see how many were blocked, how many passed, and then you can hook them up with your alerts. And then beyond that, I think someone had mentioned LangChain and LangSmith a while ago. So while those kind of systems do allow you to do tracing, what's really important is to really go down into at the metrics level, and at every step of your trace, you should be able to see whether, say, something hallucinated or not. So Galileo's detailed tracing it sort of provides you that. But there's one big challenge that we've seen emerge as folks have started using systems like Protect, which is the need for a lot of these metrics for evaluating LLMs. If you've read the literature, they sometimes rely on other LLMs, and that can get extremely expensive at scale. So one of the big challenges is how do you build evaluation metrics that are, of course, cost-effective, extremely low latency, because now you're literally applying these metrics in real time in your applications. But also you don't want to lose accuracy. I'm going to talk about hallucination as one example of the key metrics which are used. If you've read any literature on hallucination detection in 2023, a lot of the techniques that were talked about, a couple of examples include self-check BERT and these self-check techniques. They relied on other LLMs to be able to determine whether an LLM input-output pair is hallucinatory or not. And these methods got very, very expensive. Just to quote an example, one of our customers, they're a very large education company, and they have a production system which is leveraging LLMs, which is running at about 80 queries a second, which is reasonable by some standards, but some would say it's very, very lightweight. But even at that level, they have 16,000 queries average, tokens on average per query. Their hallucination detection costs using self-check techniques have gone to somewhere between $1 and $5 million a year, which is insane. And you might have budgets like that, but you'd rather use it for something else. So evaluation costs have severely gone up, especially around techniques where you're using other LLMs. So what we've done, I want to walk you through our hallucination research story, which includes a lot of work we did in 2023, and then more recently, how we've gone down solving the challenge of not relying on other LLMs or essentially reducing the cost of hallucination detection to $0. So rewinding back to our first hallucination detection method, which we published about, there's a research paper we have. You can essentially just Google this method. It's called ChainPoll. And this was created by us. It's a framework to detect hallucination, which improves or ups the ante on just asking another LLM or these self-check methods. I'm going to walk you through how we sort of came about with this method. But essentially, ChainPoll, which is the hallucination detection technique, combines two things. One is chain of thought prompting and ensembling or polling. So the intuition is that, number one, you can use chain of thought to really go dive deeper into the reasoning process of the output given the input. And you combine that with ensembling, or you do reruns to sort of measure how much difference there is between each of the runs. So the intuition is that if a response is not hallucinatory, the response, the difference across reruns will be lower. So it combines these two techniques. So just to walk you through the algorithm itself, here's how it works. So you have the user that makes a query to the LLM. You get a completion or the response. And in some cases, you get some of the details, like the log probabilities of the tokens, along with the response, which you then, in some cases, you might get it, sometimes you might not. So if you do get it, you pass it into what we call the detailed chain of thought module, which does the whole chain of thought prompting and ensembling. If you don't get the log probs, which is true in many cases, say you're prompting GPT-4, in many cases, they would not return the log probs. There's many OpenAI models, as well as others, who don't return you these details. So there's another module that we created, which is able to generate log probabilities even in the absence of it, and passes it to this ensembling module, which essentially acts as a judge, right? So there's a number of judges who sort of say yay or nay on the input-output pair, saying that, oh, this is hallucinated versus this is not. And the secret sauce is really the prompt that we worked on in this case. But it was not just the prompt. The whole framework is around this thesis that you want to use chain of thought, but you want to do reruns and you want to do ensembling to be able to really hone in on whether something's hallucinatory or not. And then, of course, these are all plug-and-play modules. You can replace the chain of thought model. You can replace the number of reruns. Those are all hyperparameters to the framework. But it really gives you a very highly accurate score of whether something's hallucinated or not. So this was the first set of results that we published, comparing ChainPoll with a lot of the standard hallucination detection methods back in 2023. This is around the fall of 2023, and we achieved significant performance improvements, say, compared to a self-check BERT or self-check Ngram, and these were the standard ways people did it. And of course, we saw it was more accurate. Because we used LLMs, we were also able to generate explanations. So it was very useful for folks to not only see whether something's hallucinated, but also understand why. It was fairly low latency because we used things like batch inferencing to essentially make one LLM call and do all of the things that I talked about in a single call. And of course, with the single call, it reduced the cost. So this was the state of affairs before we ran into challenges once Protect started getting used. That's when we introduced or ran into this challenge and thought, how can we not rely on LLMs to determine hallucinations? And which was a tall order because we did so many experiments and we really saw that these LLMs are extremely powerful and it's hard for a traditional model to be able to give you these kind of sophisticated explanations and just do open-ended hallucinations. Like, how do you solve the problem of, like, what is the capital of France versus some RAG-based hallucination? Like, it's scaled really well. So that was one of our realizations, but this was a challenge because folks would not want to do, even ChainPoll, even if it's one extra call. It's very high latency. You make these API calls, it generates a bunch of things. It just takes like 6 to 8 seconds, which is, if our ambition is sub-second, then it's a tall order. That's when we started working on what we call Luna. And Luna is very interesting because our goal was to figure out hallucinations and detecting hallucinations without the need for LLMs. So we went back to the old school language models, essentially started looking at BERT and the similar sort of category of models in the 100 to 500 million parameter range. And we reduced the definitions of hallucinations to only RAG-based hallucinations, which is the quality of the context and how much is the output sticking to the context. So we had to really tone down what we mean by hallucinations. And RAG is pretty much the de facto industry standard design pattern which folks are following. So we did a few things. We went to smaller foundation models at the core. This is the most interesting bit. We reduced the, or we took the problem of hallucination and redefined it as an entailment problem. So if you've worked on NLI models in NLP, it's a three-way classification model or classification task, which essentially takes two pairs of sentences and it tells you whether one entails the other or contradicts the other or is just neutral. And they're great NLI models, which are very, very small, and they really, they perform very well. So in the context of RAG, entailment makes sense in terms of hallucination because you have your prompt, you have your context, and you have the output. And if there is entailment, it essentially means there's no hallucination. That's the intuition. So that's where we went down that route. We trained a slew of small models on a bunch of industry vertical data. And we were actually able to outperform even Chainpool with a 400 million parameter model only in context of RAG-based hallucinations, of course. And compared to some of the other competitors or other metrics which are used, we significantly outperformed. It's close to 80% accuracy, which is quite a feat in terms of, I can share the benchmark data sets with you in the coming slides. But some of these charts that you see, so there's two main problems here. One is that of latency. So this is a 400 million parameter model just running locally. So you can see that it's essentially sub-second. We were able to bring it down to, it's 980 milliseconds, which is still, there's a lot of work to do to get it further down compared to, say, like 6,000 milliseconds and some of these LLM-based techniques. So significant win there. And then you can see over here, this is the cost. So this is essentially the cost of running an L4 GPU for a year versus if you're prompting these LLMs to determine hallucinations, they have literally gone in the millions of dollars. But all while you can see the accuracy has been maintained, which was, of course, at the end of the day, if you're not detecting hallucinations, it doesn't matter how cheap or how fast you are. These are some of this is like one section of the data sets that we used to benchmark and evaluate. And we saw some very interesting results, just to highlight a few of these. So there's three of these metrics that you see. These are in our RAG suite of evaluation metrics. There's 4 metrics that we offer. 3 of them are, one is completeness, utilization. Utilization is how much of a chunk is utilized in an answer. And relevance is how relevant is each chunk to the answer. And completeness is how complete is the answer. Like say if you ask what is the capital of France and Italy, and say the LLM answer is just Paris, that's an incomplete, just an example. But the suite of metrics together kind of tell you the overall quality of your chunks, the quality of your output, and the quality of your input. So this essentially matters because there's the whole triad of low latency, low cost, and high accuracy. And that's a tall order. But essentially that's come down to, like, that's the only way we can productionize safe LLM systems. And Luna is the first step that we've taken towards building low latency methods to detect hallucinations. And we're constantly trying to up the ante on improving the accuracy of it. There's a lot in Galileo's sort of suite of metrics that we offer, and we sort of categorize them as, the first category is that of detecting hallucinations. If you were to sort of take different, I guess, areas of how to measure hallucinations, the first is, of course, the output, how much it is adhering to the context, which is the main thing. And then beyond that, how correct is the output, how uncertain the model was while spewing out the output. These are just dream machines, right? Token machines. So all these together kind of form the slew of hallucination metrics. We also give you RAG quality, which includes the completeness of the response and how much of each chunk and each piece of context is actually being reasoned or taken into account while giving an answer. All the quantification of all this helps a lot because what we've seen is, even to Bob's point, there's newer ways people are using RAG to make it more bidirectional. They generate embeddings and feed it back. So the vector store is evolving as well. But you don't want to put every single item that's generated back into the vector store, then it's just garbage. So you need a way to quantify how good or bad the output was and make a decision on, to evolve your vector store accordingly. So all these metrics help a lot in, taking those decisions. And then there's, of course, we work with big enterprise, so safety is a huge concern. So we've built, in line of the NLI models I talked about, we've built very robust models to detect PII, tone, leakage of prompt injections and toxic data, et cetera. So anyway, this is how we kind of categorize our metrics. And along with that, no platform is a platform if you don't allow customization. So we allow you to add your own functions into the platform as metrics. So come to essentially, this week we have a slew of $0 metrics is what we call them. And they are powered by all these local small ensemble of models. We call them EFMs, or evaluation foundation models. And they run locally in your enterprise, VPN or wherever you run your system. And then we also offer these AI-powered metrics using Chainpool. That's it. I would love to connect. My name is Atin, and you can reach out to me at atin@rungalileo.